ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. We're going to get right into it today. We're going to take a look at QuaCK tables. This is the way we commonly refer to them in my class. Really what they're known is QuaCK tables, but the acronym makes it easier to remember. And so a QuaCK table, to use it, and what we're going to be able to do with it is we're going to use these tables to solve for equilibrium concentration. So again, make sure that you get down the purpose of what we're going to do with these things. Right now, highlight it, make it really big. We're going to use QuaCK tables to solve for equilibrium concentrations. And so by now, we've been looking at a lot of these values in our class, and we've been solving for Q. Well, we understand Q are these initial concentrations that we don't know whether or not we are at equilibrium, all right? But we can take them, plug them into an equilibrium expression. We can figure out which direction the reaction is going or if we are at equilibrium already, all right? And so we have to understand that with the Q values, if it's not at equilibrium, all of our reactions are going to head towards equilibrium by either reducing reactants or reducing products and vice versa. All right? And so what we do is we understand that there will be some change involved going from Q to K. Now, these C values, which is the C value of the QuaCK table, these are stoichiometric changes. And so you need to understand that there won't be stoichiometry in the form of like a stoichiometry map involved here, but we will have to understand that based on coefficients, we will see stoichiometric changes according to how the reaction will proceed. All right? And then at the very end, these are my K values. So this is concentrations at equilibrium. Now, there are other things like pressures, partial pressures that we can use in QuaCK tables, but in PreAP, we're going to stick primarily to using concentrations, all right? And so understand Q is my initial concentration, C is my stoichiometric change, K are my values at equilibrium. And so now what we do is we have a tool in our belt that if we're given some values that are not equilibrium concentrations, we have a basic setup and approach to tackling a problem and calculating what those values are going to become when they do reach equilibrium. All right? So a couple of scenarios I'm going to run through you or through with you here. The first one, and you don't erase your screen, please just continue on down your page, is that we're going to take a look at a graph, right? This is going to be one of my rate graphs where I've got a concentration versus a time. The reaction that we'll look at is just the generic 2A plus B gives me C. And so I have to understand, in this graph, what I'm going to do is I'm not going to start out with any products. And so I'm going to be my concentrations way down there at 0. And then for my reactants, I'm going to start out with the exact same amount. So both of them are going to start. Well, understanding that I have all reactants and no products, I have to realize at this point the reaction is going to proceed in the forward direction. I'm going to produce products and I'm going to consume or use up reactants to do that. So what we expect just off the bat is for the concentration of my products down here to actually increase and the concentration of my reactants to decrease. So now the question becomes, we're trying to describe that stoichiometric change. What is the value or what kind of slopes are we going to draw in here? So if I go back to red and I pull up here, and we're just going to do a general C, and you can kind of tell where equilibrium is established once that concentration actually levels out and becomes constant. And so now I look back at my reaction and I see, okay, I've got a coefficient of 1. And so is B or A going to change the exact same rate as C? Well, if you look at B, it also has a coefficient of 1. And so what we would say is that the change for those two is stoichiometrically equivalent, and the rate of change will be exactly the same, even though it is opposite, right? Because my B is going to disappear at the same rate that C will appear. And so the coefficients, what they do is they give us this window into what the individual rates of change actually are. So let's go ahead and draw B in there, and I'm going to try as best I can to make this an equivalent graph, right? I'm not perfect here, but I'm trying to get the slopes on these exactly equal, and the amount of B that disappears is the exact same of amount of C that actually appears in this particular case. So now what we do is we go and we take a look at A. Well, A has a coefficient of 2. So looking at B, I have to understand that A now is going to change and disappear twice as fast as B. And so what we do is we give it a steeper slope, right? And it will actually lose more, right? More of it will be consumed in this reaction because for every 1 B that is consumed to make a product, I'm going to consume 2 A. So again, I'm looking at my coefficients to try and get the stoichiometric change. And really, I'm just looking at those coefficients, ladies and gentlemen. Don't overthink it too much, all right? And then we can still look on this particular graph and we can say, all right, equilibrium is established approximately there where the concentrations become constant because the rate of change or the rate of the forward reaction is equal to the rate of the reverse reaction, all right? Okay, and so now what we want to do is we're going to take a look and we're actually going to quantify that particular graph using a QuaCK table. All right, and so still I'm going to use 2A plus B gives me C. I'll go ahead and put states of matter on here. Everything's going to be aqueous, right? And that becomes important. We only include in our QuaCK table, so I'm going to go ahead and set it up QCK. So we only include in our QuaCK tables those items or molecules or substances that would be involved in an equilibrium expression. All right, so we exclude solids and liquids. So now again, I promised to quantify this. Let's say we start out with 1.5 molar A, 1 molar B, and no product. So again, I know my reaction has to go in the forward direction, right? Because I don't have any products, I can't go in reverse right at the beginning, all right? So I know what's going to happen. I'm going to lose reactants, right? So I would have a negative change on there. Some of them are going to be consumed, and then I would have a positive change on my product side, all right? And so generally speaking, the whole side of a reaction, if my reaction is going forward, the change for my reactants will be negative, the change for my products would be positive, and if my reaction is traveling in the reverse direction, my change for my products would be negative, and the change for reactants would be positive. So make sure you get that clear. It's really dependent on which direction the reaction is going, all right? And then what if I don't have a 0 anywhere in my initial conditions, my Q conditions? I'd actually have to set up the Q, the reaction quotient, and do a Q versus K to predict which way the reaction is going to go. All right, so now what? Now what we're going to do is we're actually going to change, everything in change line is going to be relative to X. And so what that means is I'm going to have so much of C appear, I'll have the exact same amount of B disappear, and then here I would have twice as much, again, because of the coefficient. So really important on the C line to make sure that you understand the coefficients will match, right? The coefficients of X will match the coefficients of the substances in the balanced chemical equation, and that lets us do a stoichiometric change, right? Everything will be stoichiometrically equivalent here at the end. And then the last thing is that Q plus C equals K. And so what that means is that I do 1.5 minus 2x and 1 minus x. And then I'm going to fill something in here. I'm going to say that we actually determined that there was going to be 0.5 molar of C recovered from this reaction. And so now we realize, okay, I have an equilibrium value. So what does that tell me? That means 0 plus 0.5 equals, I'm sorry, 0 plus x, there we go, equals 0.5. I was getting ahead of myself. And so you can see here that x equals 0.5. And what that allows me to do is I understand that this equals 0.5, this equals 0.5, and this equals 1, because 2 times 0.5 gives me 1. And so here I do 1.5 minus 1 equals 0.5. And so that represents the equilibrium concentration of A. I do 1 minus x, which is 1 minus 0.5, and that equals 0.5. And so that's the equilibrium concentration of B, and then I know the equilibrium concentration of C. And that'll be something, a lot of the times, ladies and gentlemen, starting out with this the first day or so of these problems, I'll give you an equilibrium concentration to help you determine what X is, and just understand there are other ways that we can do this algebraically. All right? Okay, and so now what are we going to do? We use the QuaCK table to solve for equilibrium concentrations. Well, why am I concerned with that? Well, I can actually use those equilibrium concentrations to calculate an equilibrium constant, right? So set up my equilibrium expression because we know how to write those. Products over reactants, coefficients become exponents, right? exclude solids and liquids. And so here we go. I've got 0.5 for C, 0.5 squared for A, and 0.5 for B, and that equals Kc would be 4. All right? So I've done the math for you there. Just double check that with me on a calculator on your own. But please understand, ladies and gentlemen, the QuaCK tables is something that's going to be another tool in our arsenal that we're going to be able to determine. We'll be able to use Q versus K to determine if I'm at equilibrium, and then if I'm not, I can use these QuaCK tables to actually figure out what will my equilibrium values be. All right, so big thing. I'm going to use QuaCK tables to solve for those equilibrium concentrations, and then once we have a solid foundation of that understanding, then we'll branch off into other areas of it. All right? Okay, ladies and gentlemen, if you have questions, I'll see you in tutorials for those. Otherwise, I will see you in class.